In this video, we are going to do a hypothesis test concerning the standard deviation. And we're going to do this with a traditional method of making our decision and stating our sentence instead of using a software package for it. So here, it says the standard deviation of test scores at a high school is 7.2 with a mean of 78.4. So I'm not really sure at all what I'm supposed to do yet. I'm just reading the information from the original setup. A teacher claims that the standard deviation of girls' test scores is smaller than 7.2. A random sample of 22 girls results in a standard deviation of 5.8. Use a 5% level of significance to test the teacher's claim. So when we look at this, a lot of these problems are going to look very similar to each other in the way they set up the beginning of the problem. You have to focus on what they're asking you to do at the process, at the end of the setup of the problem, in order to know whether you're doing confidence intervals or hypothesis test or sample size, and then whether you sampled from one group or two groups, and then also what population parameter they're talking about. Is it the standard deviation or the variance or the mean or the population proportion, each of these things. Once we decide what it's focusing on, we need to also make sure that we have the criteria for the type of test that we're doing, and then carry out, or confidence interval, and then carry out the process. Now here we're supposed to test the teacher's claim at a 5% level of significance, and the teacher claims that the standard deviation of the girls' test scores is smaller than 7.2. So for our null and alternate, we always need to state the null and alternate of the hypothesis test first. It's the standard deviation, and the symbol for the standard deviation is lowercase sigma. So lowercase sigma is equal to the 7.2 is my null hypothesis, and then the alternate goes along with which way we are from that. So smaller than 7.2 is saying that the standard deviation of the girls is smaller than 7.2. Okay, now that I know that it is a smaller than or is less than in my alternate hypothesis, that tells me it's a left tail test. So I'm going to draw the distribution for the Chisquared distribution. That's where you get your critical values when you're doing a hypothesis test for the standard deviation or the variance from the Chisquared distribution. Remember, the Chisquared distribution is skewed, so I'm going to draw it skewed to the right. And then also we have that this is a less than, so it's the left tail test, and this actually approaches but doesn't touch that horizontal axis in both ways. Okay, so left tail test, and the entire alpha area, the level of significance is your alpha. In a one tail test, all of that alpha goes in that tail. Okay, now the next thing for the critical values is when it's a chi-squared distribution, you have degrees of freedom. And the degrees of freedom when you're doing a hypothesis test or confidence intervals for standard deviation or variances is n-1. So our degrees of freedom is n-1. Our n is they sampled 22 girls. So 22 subtract 1, our degrees of freedom is 21. Okay? Now, the chi-squared distribution, I've given just a little bit of a snippet of the table over here. And the chi-squared distribution is, again, skewed to the right. And when they set up the chi-square critical values, it's area right is what is given in the column headings for most of the tables that you'll refer to. Always read that and then also look at the legend to see how they've set up the table that you're referring to, but most of them will be area right. Now, since my test is a left tail test, the alpha is the area in the left tail. But if that's the amount of area in the left tail and the entire area is 1, the area right of my critical value I'm looking for is 1 subtract the 0.05. So I'm going to look under the 0.95 column across from 21 to get this critical value. So we have across from 21, underneath the 0.95, that's 11.591. If you have a chi-square table out that you're looking at, make sure you look at the column headings and the row headings and see that you see the same number. So 11.591. All right, next, after we do the null and alternate hypothesis and the critical value, we need to calculate the test statistic. And the test statistic is the first time that you do anything with your information from your sample. The test statistic for doing a hypothesis test for either the standard deviation or the variance when you're sampling from one group is chi-squared is equal to n minus 1 times s squared divided by sigma sub 0 squared. Now, n is the number of your samples, so in this particular problem, n is 22, from the 22 that we sampled. S squared is, if you have the sample variance that it gave you, you just replace this s squared with the sample variance. If they gave you the sample standard deviation, that's just s, so you'll have to put that number in and square it. And then in the denominator, it's sigma sub 0 squared. So this is the value you said the population standard deviation was equal to in the null hypothesis. That's what that sub 0 is. And then again, if your hypothesis says sigma squared, you just put that number in. If your null hypothesis says sigma equals, you have to put that number in there and square it. So for our question, we have our chi-square is equal to 22 subtract 1 is 21 times S, the sample standard deviation, random sample of 22 girls results in a standard deviation of 5.8. So, and it's standard deviation at variance, so that's S. So I have to take 5.8 and square it for S squared over sigma sub 0 squared. So here I look and I have the sigma, so I have to put the 7.2 and square it. Now when you go through and do that calculation, you get 13.63. So this bottom horizontal line is a number line. Smaller numbers left, bigger numbers right. When I compare test statistics to critical values, you place them as they would fall with relation to each other on the number line. 13.63 is bigger than 11.591. So my 11.591, I'm going to write that a little bit better here. So since my test statistic is under the open region, not under the tail where the area is, this is the do not reject region. You only reject the null if it's underneath the shaded area where the level of significance was placed. So this is do not reject. So we're going to say at the 5% level of significance, do not reject the null. And if you can't reject the null, you do not have significant evidence to support the alternate. So the data is not significant to support the teacher's claim or to indicate that the girl's standard deviation is less than 7.2. So the data is not significant to indicate the girl's standard deviation is less than 7.2. And that's one of the ways that you can do the hypothesis test for the variance or for the standard deviation. Again, there's software packages out where you could do a p-value comparison for the hypothesis test. If you do that, then you have to find the p-value with the chi-squared distribution, and then go from there in terms of comparing it with your alpha. Remember, with p-value, if the p-value is smaller than the alpha, you reject the null. If the p-value is not smaller than the alpha, you can't reject the null. But with the critical value in the test statistic like this one is, you find your critical value first, place it, and then your test statistic gets placed on the number line with reference to where it would normally be on the number lines from small to large. And if the test statistic is under the open region, you cannot reject the null. If the test statistic is under the shaded region more towards the tails, that's when you do reject the null. And if your decision is that you cannot reject the null, then your data is not significant to indicate the alternate. But if you can reject the null, then your data is significant.